Okay, today we will talk about virtual memory. This is a continuation of previous chapter on paging. In this section, we will briefly talk about some background information. Then really the two most important sections will be demand paging and page replacement. And we will also talk about several other issues. The goals here is to learn about the benefits of virtual memory systems, what's a virtual memory and why we need it. And after this section, you will be able to better explain the ideas of demand paging, how it works, what are the page replacement algorithms, etc. And then a couple of other issues that are related to the performance of these systems, basically. Okay, so let's start with some background information. Quickly remember the topics we discussed before on paging. If you remember, we said a program image, right, needs to be in the physical memory so that we can run the program. And then we said the problem with that idea was having a contiguous memory allocation problem. Then the paging came and said divide this logical memory into fixed size blocks called the pages, and then divide the physical memory into same size blocks called the frames. And then we can put these pages, let's say page 1, page 0, 1, 2, 4 pages into different frames as long as we know where they are, right? Page 0 could be here, page 1 could be here, page 2 will be here, and page 4 could be here. And these transitions can be done by using a page table. Simply by using the page number as an index, we can figure out the frame number, and then by taking the frame number and the offset number together, we can create a physical address, right? So I hope you guys remember, and we will do a quick exercise on this one. Then we go to the physical address, basically. Okay, so that was the idea. But again, the problem here is, even if you are doing the paging, you need to be able to put all these pages somewhere in the physical memory so that we can run the program. And now the question in this section that we are going to address is, what if the program image is larger than the physical memory as physical memory? And I think we did some exercises previously. We did not discuss that issue, but the virtual memory size was greater than the physical memory size, right? So the question here is, if that's the case, can we run the program still? Okay. Is it possible to run a program larger than the physical memory? So that's the question now. And we're going to see whether the answer is yes or not, and most likely it is yes, right? And then we will learn how to make that thing work, basically. But before that, so let's make some observation. So when you think about your code, right, when you think about your logical address space, where remember we have some code, and then we have some static variables, and then this part of the logical memory is actually reserved for the stack, for the function calls, and this part is reserved for memory allocation. So if your program makes memory allocations, then we will allocate space from here, or if your program makes functions calls, we will allocate space. But initially, actually, we don't need all that space at the beginning when to be able to run the program. So there's really no need to allocate that much space in the physical memory because we may not use all of that, right? The other part of the code we may not use at all is, remember in the codes, we have some, let's say, if something is true, right? If something is true, we will do maybe so many things. But if that thing is not true, maybe we will not execute that piece of code, right? So probably we don't need that code. So in that case, probably it's not necessary to get this part of the code into the main memory until that condition is true. So basically the idea here is most of the code may not be needed when we first start the program, and so they don't need to be in the physical memory. Similarly, maybe if you have a big array, maybe you are searching the first half of the array for something, so you don't really need the second half of the array, etc. Right? So again, even if you have large amount of data in your program, you may not need to access every bit in that data, basically. So making these observations, we can clearly guess that yes, actually, if we can find a way to run the programs without loading everything in the memory, that will be great. This way we can effectively utilize our physical memory. And that's where the virtual memory management idea comes into the picture. Okay, so let me just give you the definition for now, and then we will be talking about how that system works. It's a natural extension of the paging, and we will see the relations, and we will go from there. Okay, so the virtual memory is a memory management mechanism that allows execution of processes that are not completely in the main memory. So basically, if your program image is so large and if you have, let's say, many pages, then to be able to run this program in the physical system, you don't need to allocate space frames for all these pages. Maybe a couple of pages here and then a couple of data blocks here needs to be allocated, let's say like this, then the program can start working. And then when we need the other blocks, dynamically the operating system will bring those blocks from disks into the memory basically. And then when some of these blocks are not needed anymore, they can be put back on the disk, assuming that the program image will be available on the permanent disk where we have significant amount of memory and we don't need to worry about the memory allocation there. Okay, how that is going to be implemented? Actually, there are different ways to do it, but we will be mainly focusing on something called the demand paging. So it's pretty much the same as paging, but this time when the page is demanded, basically that's where that comes from, we will get that page from the disk, and then accordingly we will manage a paging system, and we will assume that not all pages are available in the physical memory, so they need to be brought into the physical memory when there is a need or when there is a demand for these pages. Okay, so that's the idea, that's the big problem we are trying to solve, how to run programs even they don't fit into the physical memory. And in the next slides we will just basically talk what could be the advantage. We already mentioned a couple of things, but let's, in a more systematic way, let's just mention a couple of more benefits of running programs without requiring them to be in the memory fully. So partially we can put some of the code into the memory and then we can start running the program. So what could be the possible benefits of this idea? Understanding some of the discussions we had so far, I would like you guys to pause the video for a second and try to answer that question by yourself, and then you can continue with me, and then we will show these benefits in the next slide. Okay. Okay, here are some of the benefits that comes to mind. First of all, so the user will have a very large logical address space. Okay, what is the advantage of that thing? Remember, when we are using the logical address space, if you make it small, then the programs, for example, let's say this part will go to the code, and if you make it small, then this part and this part will be limited, so the programs cannot make too many function calls because then you will not have any space, or the programs cannot create large arrays or things like this, so that you cannot run larger programs, right? So that's a disadvantage. But what we can do, but the good thing here is in the old system we have to allocate space. That's why they were keeping it small. But now, since we don't need to allocate space in the physical memory, we can make our logical address space as large as we want. So this way we can assume that this part of the memory is not going to be really allocated in the physical memory yet until we need it, right? So when we are writing our programs, they can be compiled in the context of such a large logical address space. So we can assume that our programs can have larger amount of arrays, codes, and things like this. But then when it comes to actually executing it, only maybe some of these frames will be allocated, maybe one from here and one from here will be allocated. So with 4 frame allocations here, we are able to run this program. And then as this program runs, and if it needs space here, then these pages can be dynamically created and put into the memory so that we can effectively utilize our physical memory while being able to run larger programs. Okay, so that's one of the biggest advantage or the benefit of using virtual memory management system. And yeah, we already mentioned that one. Users can execute programs that are larger than the physical memory. Otherwise, that wouldn't be possible in the old systems, because in the old systems we had to put everything into the physical memory. Another thing here is actually another nice thing about this one, since we can run a program with a limited number of pages in the frame, then we can support multiple programs, right? Because previously we had to put every program into the memory and we may not have enough space in the memory. But now for every program we just need to have maybe a few pages from program 1, a few pages from program 2, a few pages from program 3. So we can increase the number of programs that can be supported by the operating system, and that will effectively increase the multi-programming level of the system. And remember, in the first few lectures we were talking about is multi-programming, and if you increase the number of programs in the system, then you will better utilize your CPU basically. Okay, can you think of any other benefits? So these other ones are also important, but I will just mention this and let you guys to read them from the books. So it will also allow us to have less input-output to load or swap the user program. So basically here the idea is, remember once I was talking about swapping, and if we said if we get too many programs into the physical memory, let's say this is the physical memory, right? And if another program comes in, now we cannot run this program until we swap out one of the programs back on the disk, right? Then we can install that program and run it. But now with the paging, with the virtual memory paging, actually we don't need to do that whole thing because it's so expensive to copy this on the disk and then bring back from the disk into the memory. We can have some pages from this program, some pages from that program, and some pages from this program, and now we have enough space to support that one as well. And then, since not all parts of these programs are needed, we will be effectively using our physical memory. So that will be really good when we are also swapping the programs out to get new. And then if some of these pages are needed, right, we can bring them back from the disk, only the pages, not the whole program. So that's why input-output of swapping will be really fast. And we can also say a couple of words about the physical memory allocation and the allocation. Since we are giving a very large logical space for users, they can write their programs and assume that they have significant amount of memory, but then the operating system can easily and effectively manage the frames and dynamically allocate those spaces. Okay, I'll let you guys look at these ones from the book as well. Okay, so let's continue with, yeah, I mean, here the whole idea was if you compare this with the traditional swapping, the virtual memory paging is much faster, much better, because you are only swapping the pages from one program to another program instead of the whole program swapping. Okay, so it will be much faster and efficient. Okay, so let's look at a little bit carefully the virtual memory things. And so basically this is a little bit background information. It's pretty much related to the logical addresses, virtual addresses, things we discussed before. So this is the logical address of your program, or the virtual address space of your program as a user when you are writing your program. That's how you see your program, right? And then what we said with the paging, we don't because we don't want to have the operating system to allocate a contiguous space to put such a large amount of information, right? What we did, we divided that space into pages, right? So we divided this space into the pages, and then we put each page into the physical memory. Let's say this is our physical memory, right? It's also divided into the same size blocks. We call them frames in that case, right? In this case, we call them pages. And then by using a paging table, we were able to assign each page, right, to somewhere in the physical memory, right? And they can be anywhere. They don't need to be contiguous, basically. Okay, so this is the big picture, and what we are going to discuss in that context is pretty much a natural extension of that paging idea. And the nice thing here is when we do the paging in the first chapter, tk7 or SGG chapter 7, we were assuming that we are allocating space for these blocks as well. But actually now with the virtual memory things, what will happen is we will only allocate space for the data, for the code and data blocks that are needed. We don't need to allocate space for these things until we really need them. And when we need them, then we will start allocating space for these pages in the physical memory. Okay. Okay. And basically the idea is when you have a virtual address space or the virtual memory for your program, of course we will assume that you have such a large space, and then you will allocate that such a large space on the disk basically. Okay, so we are assuming that all that information will be available on the disk, and then when we will put these things into the physical memory, what we are going to do is we will, as in the paging, we will assume that you have a memory map or a page table, which simply tells us, using the page number as an index, we get the page number, and then from here, for example, we know that this page is on that physical disk, and then by combining the offset number with the frame number, we go to the physical address within that frame. But some of the pages here will be not on the physical memory, they will be on the disk. So this way we can access them as well. And how we really know that one? So remember in this page table we had some control bits. So one of these control bits was valid, invalid bit, right? So if that bit is set to the valid bit is set to 1, then it means that this page is in the physical memory. If that bit is set to 0, then it means that page, this frame number here doesn't make any sense because that page is not in the physical memory, it is on the disk. So if you are trying to access anything in that page, we have to first go to the disk, and actually the operating system goes to the disk and gets that page somewhere in the physical memory. Let's say it assigns that frame to this page, and then accordingly it updates this frame number so that this frame number will refer to that frame, and then it will change valid invalid bit to the one saying that this bit is valid. Now we can do the traditional page translation basically. Okay, so we will discuss that idea one more time, but that's the whole idea basically. So everything is available for the program image wise on the disk. Okay, and then in the physical memory we do not allocate space for every page, but in the page table of course we have to have an entry for every page, and for some of the pages we will have that control bit as 1, some of them 0, 1, 0, 1, 1, 0, 1, whatever. So the 1 means this page is in the disk on the physical memory. If it is 0, then it means this page is not available in the physical memory, it's available on the disk, and we know where it is. So first, before resolving the address, we have to first get that page from disk into the physical memory, and then we can just do the address translation as we did before. Okay, we will come back and visit that idea one more time. And once the page is in the physical memory, then the address translation or the address conversion is done as we discussed before, and we will see a quick example now. Okay, so this is just a background information, and as a good reminder and a good exercise for the previous chapter. If you remember, we divide our logical address space, right? So let's say this is our logical address space into the pages, and then we also divide our physical address space, right, into the similar size blocks where we call them frame, and here we call them pages, right? And then we also learn how to, when there's an address here, right? Let's say for example for this byte, if there's an reference for this as an address, right? So we learn how to translate that address into the physical address, which could be somewhere here. Let's say how to access that one, right? So we learned that one, and that's the idea. We will discuss in a second, and this was the idea. So the CPU generates the logical address, memory management unit by looking at the table, finding out the corresponding frame number, and then combining the frame number and then the offset number we generate, you get a logical address, you divide that into page number and an offset, and then by using page number as an index on a page table, we get the frame number, and then we combine this frame number and offset number to get to the physical memory. So that's the idea as before. Okay. Okay, so how we do these translations, I think we already discussed, and I think you can pause the video for a second and try to remember how we did that one first. Then we will do the exercises in the one exercise, I think, in the next slide. Okay. Okay, so here's one example. Assume that the virtual memory is 64 kilobyte and the physical memory is 32 kilobyte. See, the virtual memory of any program is greater than the physical memory. So clearly we cannot put everything from this any program in this system into that physical memory. So definitely we need something that allows us to put only some number of pages from any program into the physical memory and be able to execute it. Okay, so that's a good example where you need virtual memory management systems. But anyway, so we will discuss that in a second. For now, let's just focus on the previous chapter related address translation issue. Okay, and the page table size is given as 4 kilobytes. So first what we need to do, if you remember, we need to first find out what is the representation of this in terms of 2 to the power something. Okay. Okay, so 64 is 2 to the power 6 and kilo is 2 to the power 10. So altogether is 2 to the power 16. That's where this 16-bit comes. Okay, so you need 16 bits to address every byte within that virtual memory. Similarly, this 32 kilobytes, so you can write it like 32 is 2 to the power 5 and kilo means 2 to the power 10, so that means 2 to the power 15, right? So this 15 bits is the number of bits that are needed for physical addresses. So, and similarly for 4 kilobytes, we can write it like this. 4 is 2 to the power 2, kilo is 2 to the power 10, so it is 2 to the power 12. So these 12 bits are needed to address every byte within a frame, which, if you remember, that was the number of bits for your offset, basically. So now if you know these numbers, then it's very easy to find out how many bits I need for page number and then how many bits I need for frame number. Okay, pause the video for a second and tell me these numbers. Okay, I hope you got the same numbers, and then we can compute how many pages and how many frames we have. Okay, so let's just look at this one first. So since we have 16 bits in our virtual address space, right, we can use the 12 of them for offset. So the remaining 4 bits will be the number of bits for page. So the P is going to be 4-bit basically. Okay, and for the physical address we had 15 bits and we used 12 of them for offset. Then the remaining 3 bits will be your F bits. So you need that many bits for frame number. So that's basically the system design for this case. Okay, so now the next question here is, we need to be able to do this translation, we need to have a page table, right? And remember, the page table should have one entry for each page. So how many pages do I have in that system? 4 is the number of bits, is not the number of pages, right? The 4 is the number of bits that you can address each page. So with 4 bits, we can address 2 to the power 4 many pages. So in this system, we have 2 to the power 4, which is 16 entries in the system, okay? And how many frames do I have? Again, it's not 3 frames. You have 3 bits to address every frame. So then it is 2 to the power 3, which is equal to 8 frames you have in that system. Okay, so now by using these 4 bits, we will be able to generate 16 different combinations, like starting from 0, 0, 0, 0, which is the address of, let's say, this frame, and then 0, 0, 0, 1, which is the address of this, and then goes up to 1, 1, 1, 1. So that's the last page, basically, right? Because 0, 1, 2, 3, 4, and 15, and total we have 16 pages. Okay, so now by using these 4 pages, right, for these 4 bits as the page number, we will access whatever it is to that page entry, and then within that page entry, what do we store? We store the number of bits here. Okay, so we have this number of bits, we will get this number of bits, and then we copy the offset bits together, and now you get your physical address basically. Okay, and that's pretty much what you need to do for your assignment 1 part 1. Based on the given system parameters like this, you need to figure out what these bits are, how many bits you need to use, how many bits you need to use for your P, and how many bits you need to use for your frame number basically first, using the C language. Okay, so let me stop here for a second. Okay, now we have a good understanding of a general virtual memory management system, and we also just quickly reviewed the key ideas from previous chapter, how to resolve a logical address and map it to a physical address, right? And the key idea here is we were putting all the logical pages into the physical memory, but actually the idea behind the demand paging is just put only the pages that are needed for the current execution or the current code to be successful in processing the given data, right? So only we need those frames and how that system will work. Before getting into the details of demand paging, I would like to just compare it with the swapping that we discussed before. So demand paging versus the swapping idea was this, okay? So in the physical memory, in the old days, they had all the program, all the pages of that program and all the pages of that program. And if you like to remove that program from the physical memory using the swapping, you have to copy everything into the disk, and you have to bring back everything from disk into the physical memory. Now with the paging, basically what we are doing is we are only swapping out some of the pages that are not needed anymore, and then we are only bringing the pages that are needed for the current execution. So that's where the name comes from. Upon the demand, we will be loading new pages into the memory. As we discussed before, there are several advantages of this compared to the swapping. First of all, it will be really fast, and it will be very efficient in terms of input output, because you only swap out and swap in the necessary pages, and you don't lose the control of the whole program, and both programs are still be able to execute under virtual memory management. Okay, and with that, of course, we can support more users. And to control what's happening here, basically, in addition to our page table we had before, right, we will have a control bit here called the valid invalid bit, and that bit will tell us whether that given page is in the physical memory or not. And if it is not in the physical memory, then we will go get this from the disk into the physical memory. And also when we are swapping out certain pages, for example, we can use one of the for example, we can use one of the other control bits that's called either a reference bit or a dirty bit. If during the execution of the program, let's say if this page is changed or if that frame is updated, then definitely when you are swapping out, you need to write it back onto the disk. If nothing is changed on the frame, right, the copy on the disk is the same as this one, so there's no need to copy. So you can do also this type of little optimizations with demand paging. Okay, so now let's probably this is one of the important slides. We already mentioned the general ideas, but let's just discuss it one more time using step-by-step instructions on how the pages are brought into the memory. Okay, so when we are running a program, of course, the copy of our program will be on this is the logical address space of our program, and all these frames will be on the disk as well. And when we are running the program, of course, we have a page table here. In the old system, we had to load everything into the physical memory, right? And then we have to find out what's the frame number for each page. But now we don't need to put all the pages into the physical memory yet unless they are needed. So we will assume that some number of frames will be needed, and the other frames will be brought into the memory as needed. We will see in a second. Okay, so let's start with this. Assume that somehow the operating system knows that it needs to have this page A and this page C and this page F in the main memory. So what it will do, it will bring those pages from disk and then assign one of the available frames and put the frame number here. So for example, for frame 0, it puts 4 here and it sets that bit to valid bit. For B, for page number 1, we don't need it yet, so it's going to be invalid and this value doesn't matter, right? So for the page C, which is page 2 here, so we find out it is somewhere here, right? We get that one and put it here and we assign this frame, so we put 6 here, etc. Okay, so now with that translation, basically what happens is when there's an address, let's say here, right? Remember what we do? We divide that into the P bits and D bits, depending on our system configuration. And using these P bits, we get into this entry. And since that entry is valid, as before in the previous chapter, we take this number 6, right? 3 bits, and we copy this D bits here. And now you get your physical address to access the data. Okay, so that's how simple it is. So that's same as before. Where the things will be different is this. Okay, so when, let's say, somehow here one of the instructions when you're running wants to access, let's say, a byte here within that page. So now again we're going to take that. Let's look at a case where these pages are in the physical memory. So any address, as we discussed, that references within these pages can be easily resolved, as we discussed before. Right? But let's say now there's an address request within that page, right? So when we do the as before, so when you get this logical address, let's say you get this logical address, right? So you would divide that into 2 parts, P bits and D bits. And then by using these P bits, which is page 4, you access page 4, right? But unfortunately, the page 4 entry is invalid, so we cannot really resolve this address yet. So what we need to do, actually the operating system needs to do is this. When it realizes that this is invalid, then it causes a page fault. It's in like an internal interrupt, and the operating system handles that interrupt as follows. Okay, so basically what it does, it saves all your instructions and everything in your program part, and then the operating system takes the control and it simply goes into the disk for this page 0, 1, 2, 3, 4, right? So this is the page we are talking about. So this page needs to be copied into the physical memory so that we can use it, right? So the operating system will search one of these frames and find an available frame. Let's assume it finds this as the available frame. Then it will copy the content of this page here, whatever it is, and then it's going to update the page table saying that, okay, page 4 has the page frame number 12, and it also updates this one and says now this is valid. And then it gives control back to your program, which the instruction was stopped, right? So that instruction will be renewed. So let's say when we try to access that address one more time, same idea. We will come back. We will divide that into the P bits, D bits, depending on our system configuration. And now by using this P bits, when we access the page, it's valid. Okay, so now we can take this 12 of frame number. We will put 12 here, F bits, whatever it is. And then we will copy this D bits here. And then we will get this, and now finally we get our physical address, so we can go and access the corresponding byte within that system. So that's all the things that is we need to do about demand paging. Okay, so that picture just gives you the whole idea one more time, what happens when we encounter an invalid page entry. Okay, so we get an reference, so that's the number 1. So we go by, let's say we got a reference for this address, but on this logical address space, but let's say this page is not in the system because the corresponding entry has an invalid entry, right? So in this case, we get this is the first step. When we realize that this is invalid, then the system will cause an internal interrupt. We call it a page fault, basically. When that page fault happens, operating system takes the control and saves everything about your process. We know how to do the context switching, right? So then it basically goes into the operating system, and then the operating system simply goes to the disk, gets the corresponding page, whatever it's from the disk, and then it copies into one of the available frames into the in the physical memory. So the operating system needs to also keep track of which frame is available so it can assign that frame, and then based on this assignment it updates the page table. Okay, and then now it gives control back to the program so the program can restart its last instruction, and then hopefully now this time, since it will be valid, as we discussed before, it can simply resolve the address translation. Okay, we discussed some the basic ideas on the demand paging, but actually in real implementation there are a few complexities you have to deal with. For example, let's say you have an instruction says read the data from variable A, variable B, and add them and put the results into the C. So in this system, for example, if each of these variables are in different pages, right? Let's say A is somewhere here, B is somewhere here, and C is somewhere here, right? To be able to successfully execute this instruction, system should be able to get that page, and that page into the memory. Otherwise, it cannot execute that statement, right? So there are some minimum number of pages every program should be guaranteed so that it can run, but that depends on the architecture. Okay. Another complexity here is what happens if you are trying to move a block of data from one place to another place in the memory, in the memory, right? So in this case, again, all these things needs to be in the memory so that you can successfully execute that instruction. So these are some of the details you can also read from the book. Okay, so let's finish this section with one maybe an possible exam question, like how the page fault is handled, right? So you're expected to, let's say, address or be able to explain the picture we just showed here, right? So you should be able to explain what happens in case of a page fault. So basically we will assume that we have a logical address. So you have a logical address generated by the CPU, right? And you get here to access something, but what we do, we look at the page table for the corresponding entry. If this one is invalid, then what we need to do, okay, we generate a page fault trap, right? And now the operating system gets into the business, and the operating system goes and let's say this is our actual frames here, goes into the disk and gets that corresponding page from disk into the physical memory and finds out what's the frame number here. It then copies that frame number here and makes that bit valid, and then now it gives back control to the process. And now when that address comes in, now it is valid by taking this F bit, right, and then by combining of course, now when this comes in, we divide it into P bits and D bits. By using these T bits, we go here, get the F bits and copy it here, and then we copy these D bits here, and now you got your physical address to access the memory, basically. Okay, so let's stop here. Next time we will talk about some page replacement algorithm, and that's probably the most complicated part of this section, I would say.